Good morning, students. This is about the vector integration calculus and its applications. Uh, we do a few problems on gradient operator, divergence, and curl operator, and then we try to apply Green's, Stokes, and Gauss divergence theorems to solve some problems. So here see, we will have a quick view of the uh, definitions for the gradient, divergence, and curl operators, and then we quickly move to the. We will recall the statements of Green's theorem, Stokes theorem, and Gauss divergence theorem, and then we subsequently move for the problem solving session. Yeah, see here, when we talk about the differential operator, vector differential operator, we are talking about a vector. We are dealing with a vector field f bar, and r bar is considered to be the position vector, and then you have see something like uh, f of r bar. That is, I mean, see here. Uh, See what I mean to say is that. Okay, so our here r bar means always you have xi bar plus yj bar plus zk bar. This is the position vector. Then we deal with the two types of functions as before we told. One is called scalar field, and the other is called vector field. Vector field. So sometimes the same disposition vector can also be represented as like this. And this already we have discussed in the previous session. And also people may write like this: x into ex cap, that is the unit vector here, I bar, j bar, k bar are the unit vectors along x axis, y axis, and z axis when we are following three-dimensional Euclidean space. So in place of I bar, j bar, and k bar, sometimes those three vectors, unit vectors, can also be represented by ex cap, ey cap, and ez cap. So this already we were told. So we are in for now throughout this session we are dealing with three dimensional Cartesian space. So you have a vector here like this x y z. Then you can, this is the vector we are talking about, r bar, and you can think about the unit vectors along x-axis, along y-axis, and along z-axis. So this is usually represented by I bar, or ex bar, and this is j bar, and this is k bar. This is how the representation will be. And then when we deal with the scalar field, I mean scalar field, scalar field, I mean here, scalar field, I mean here. Uh, so usually, if we represent that by, I may write this as phi of r bar. So that is basically a number. It is a scalar number. When you are talking about vector field, we may put bar or may not put bar. It is understood whenever we are putting bar, it is for simplicity's sake we put that, easy to understand. So this is a vector valued function. Then, as I told you, this has I bar quotient along I bar and along J bar and along K bar. You can resolve that one. You can project along that idea. So the components you can get, and some people may write like this: F1, that is a function of x y z into I bar, plus F2, that is a function of x y z into J bar, plus f3, that is a function of xyz. It's a real valued function into k bar. This is r, p into I bar plus q into j bar plus r into k bar. That is, the respective components of f bar can either be uh, represented by f1 comma f2 comma f3, where each of these f1 f2 f3 are functions, real valued functions of xyz, or capital P, capital Q, capital R, where each of the functions capital P, capital Q, capital R are functions of x, y, z as mentioned here. So when it comes to gradient, it is defined like this. The grad phi, we call it grad of phi, that is for scalar function. So it is del operator. See, del is equal to do by do x plus do by do y plus do by do z. And people may represent like this: ex, e subscript x means in place of e subscript x, please remember we can use I bar. In place of e subscript y, we can put j bar, and in place of e subscript z, we can place k bar. So accordingly, that is I bar into. So you can write this operator like this also if you use IZK notation. So is equal to I bar into dou by dou x plus j bar into dou by dou y plus k bar into dou by dou z. This is the del operator, or I call it vector differential operator. Now see, with this one, we have clearly defined what is grade phi. Grade phi means dou phi by dou x. See, if I ask you what is grade phi here, it is phi is a scalar function. So phi, if one treats phi of x y z as a scalar field or a scalar, I mean real valued function of a vector, so people may call it this is scalar field. So in such a case, we have grade phi is equal to uh, dou phi by dou x, that is phi x me into I bar, plus phi y, dou phi by dou y into j bar, plus dou phi by dou z into k bar. This is what we have. Now, when we shift to the other one like divergence, for divergence you need to deal with when you are talking about either divergence or curl, we are talking about, we are dealing with the vector differential operator along with a vector field, along with a vector field. So in such a case, you have f bar in short, you can either take like this for okay, where PQR are functions, real valued functions of XYZ. So in such a case, if I write divergence of F bar, people may represent this as this also can be represented like this, nothing but Px, that is dou P by dou X, P subscript Q subscript Y, that is dou Q by dou Y, plus dou R by dou Z. This is how this can be represented. And then we can also represent, we can also I mean, there is another idea called curl of F bar with regard to uh, right, with regard to uh, vector field. So in such a case, as before, quick recall I am doing here, you can think about a determinant k bar here, and so you can write like dou by dou x, dou by dou y, dou by dou z. Okay, then we have F P Q R. This can in short be written as, after expansion I mean, this can be written as is equal to, you have C Ry, that is dou R dou Y, minus Q Z into I bar. Now I told it, I mean circular summation. After R, P will come PQR. See, you have PQR. This you imagine about this circular triangle, and you have X, Y, Z. And also you can think about I bar, J bar, K bar. With all these things, three triangles, you can think about the circular summation. With regard to curl only I am talking about. So this is one triangle, this is another triangle, and the third triangle is this. Okay, so after R, after RP will come, after YZ will come, minus again R, after ZX will come. Okay, you have after I bar, J bar will be there, and then plus after PQ will be there, QX minus QX minus after RP will be there, Y K bar. This is curl formula, I can remember. Okay, then see, uh, there is some some a few of the meanings I will tell you. So whenever you are talking, see, when you are thinking about a real valued function of a of three variables, that is of a vector variable, I call it. This is a scalar field. What we are saying, a scalar field. This is known as a scalar field. That also can be uh, viewed as a real valued function of a vector variable. So I mean, please remember that this vector can be viewed as phi of r, I mean r bar. So phi of r bar, you can imagine like that. So, and this function can also, so whenever, see, you are talking about something like this, then this is also known as level surface. It represents a surface in three space. Okay, for example, you have x square plus y square plus z square is equal to say 4. So what is this? What does this represent? This represent a sphere, okay, centered at origin. Where is that origin? This is the origin. And with radius 2. Okay, with radius 2. Now, uh, right, with radius 2. So, if we consider this as our phi, if we consider this as our phi, if we consider this as our phi, then grad phi, then grad phi, how we write like this? Nothing but, see here, dou phi by dou x, that is 2x I bar plus dou phi by dou y 2y j bar plus dou phi by dou z 2z k bar. So this represents a vector. You can write like this: xi bar plus yj bar plus zk bar. This is known as normal vector. So this represents normal vector to the surface to the surface phi of xyz is equal to c. Okay. So this is a use of an application of gradient. This can be viewed as an application of gradient. So if you have a level surface or phi of xyz is equal to c, like x square plus y square plus z square is equal to 4, then you can think of at any point xyz the normal is given by this one. So if I want a unit normal, see here, if I want a unit normal, so you need to know what is norm of this one here. It is simple. I recall. So norm means length. You can think like that is equal to, just now we have calculated xi bar yj bar plus zk bar. So if you do, you can pull out that being a scalar. So length is, all right. How can we define this one? This is nothing but square root of x square plus y square plus z square, that is the sum of the coefficients of I bar j bar inside this one, I bar j bar k bar, there x y z, sum of squares of I bar j bar k bar. So but we are on the sphere, so 2x square plus y square plus z square is it is 4. So you have 2 into 2, it is 4. Okay. So now if I want to normalize this, so what I will do is that we'll take this, sorry, normalized vector I am talking about. This simply multiply by this number. So just now we have seen that number to be equal to 4. That number equal to 4. So So it is 1 by 4. Okay. You have 2xi bar plus 2yj bar plus 2z k bar. Okay. So this norm is 1. See, if you take, this is also known as unit normal. This is known as unit normal. So you can write like this. Okay, unit normal vector 2, unit normal vector 2, the surface is equal to C. So this is another thing that to be noted. And subsequently, to the next of this, yeah, there is something called directional derivative. Okay, this also, from this also we can find some important questions. So what is the meaning of this? See, if you remember the formula, it is enough. Directional derivative means we are thinking about first, see what to be given, what will be given, and what you are asked to find. So when we are talking about directional derivative, they will give a point P of x. So I write better. They will give a vector ABC. Then they will also give. We are also given. This is called. Okay. See here. This is, you treat this as a point A. Okay. And then will be given a vector. Okay. That vector, how do they represent? Right. That vector, this, okay, good. That vector, I say A bar is A1, A2, A3. See, this is a point. Remember, this is a point. This is a vector. So how can we write this? We can also write this as A1 I bar plus A2 J bar plus A3 K bar. You can also write like this if you want. So now we are talking about, there is there will be a function also. 1, 2, there will be a function f. See, this is okay, we will take a scalar function. Don't take a vector function. So scalar valued function. Now we are talking about the directional derivative of phi in the direction of a bar, I mean along a bar at the point A, capital A, ABC. How that can be written? So see here, so that is nothing but 1 by mod A bar into A bar grad f. See here, that directional derivative is given by 1 by mod A bar, that is norm of A bar, into A bar, okay, dot grad phi. That is what is said. This is called directional derivative. Okay, so what is this grad phi? We knew that this grad phi is phi x I bar plus phi y j bar plus phi z k bar, dou phi by dou z I mean k bar. And what is your a bar? If you look at your a bar, if you look at your a bar is a1 a bar plus a2 j bar plus a3 k bar. So if we make the dot product, this becomes, if you think about if we think about the dot product, this becomes 1 by a bar means what? Square root of a1 square plus a2 square plus a3 square into, now you write C, a1 into phi of x plus a2 into phi of y plus a3 into phi of z. Okay, but we want to calculate directional derivative at which point? At capital A. So wherever at capital A. So wherever you have in this, you see, basically this is an expression involving xyz. So wherever you have xyz, you in place of xyz, what we need to substitute? Simply A, B, C. That is the point we are considering capital A. So we need to consider this, right? So this is known as directional derivative. That is one more important concept here. And then subsequently, then next to that this, okay. So I talked about curl, okay. As I told before, divergence of curl is f bar is 0, curl of grad phi is 0, curl f bar is grad div f bar minus this del f. Okay, so you need to remember also, that also, right? Okay, right. Now see, okay, I have one more thing. You need to remember one thing. There are two things will come here. One is, okay, right. So if you are dealing with f bar, that is a, okay, vector field. People say that it is conservative. We can say that it is a conservative vector field if f bar is equal to grad phi for some scalar field. For some scalar field. Similarly, f bar, this is one angle. The other one is f bar is irrotational. F bar is irrotational. It is another, f bar is irrotational. F bar is irrotational if curl of f bar is 0. This is important. Okay. So sometimes what may happen is that you have, yeah, yeah. So if you show, yeah, right, this is enough. Okay. This is all about curves. See, so far we are talking about uh, functions of vector functions of, I mean vector variable, functions of vector variable. See, we have seen here functions of vector variables. And so how many types of functions of vector variables are there? There are two types of functions of vector variable. If the value of that function is a scalar, then it's called a scalar field. If the value of that function is a vector, then it's called a vector field. So that is the both these functions, scalar field and vector field, can be the ideas of scalar field and vector field can be viewed as a function of vector variable. Scalar field is a scalar valued function or a real valued function of a vector variable, and vector field can be viewed as a vector valued function of a vector variable. On the other hand, there are certain things called in three-dimensional space. You can think about, we come across, curves, surfaces. Whenever we talk about curves and surfaces, see a curve. An example is you can see that a circle is a curve, circle is a curve, parabola is a curve. So when you think about circle, circle is a closed curve. On the other hand, uh, parabola is an open curve. Similarly, you can think about closed surfaces and closed surfaces and open surfaces. So we are now talking about the geometric objects here of the 3D space, three-dimensional space. So when you think about geometric objects, I told, so you can move along curves or you can move on surfaces. On surfaces, I say. So there are curves, open curves, closed curves. In a similar way, we have open surfaces and closed surfaces. See, for example, if you think about an open surface, it may be like this. So, if you have a parabola like thing, then if you start rotating this parabola about z axis, then what you'll get? You'll get a shape. You'll get a shape. That shape is like this. Like this. So, see, this area is open. This is open area. So it is an example of an open surface. Whenever we think about an open surface, you can think about its boundary. What we mean by boundary here? What we can think, imagine about its boundary. So this is the boundary. The boundary is a circle here. The boundary is a circle here. On the other hand, on the other hand, you can think about a sphere. This is the standard one. This is the standard one. Like this. So this is a standard one. So it's a sphere. So sphere is a closed surface. It is a closed surface. So whenever we are talking about closed surfaces, it is natural to think about the volume that those closed surfaces enclosed. So what are the measures? See, whether if you talk about curve, see, I'll tell you one thing. If we are dealing with curves, if we are dealing with curves, if it's an open curve, see, I'll tell one thing. If it's an open curve, then you can talk about its measure. Its measure is length of that curve. When it is closed, like a circle, it encloses some area. It encloses some area. If suppose my curve is a plane curve, so it encloses area. So when you are dealing with the closed curves, you can think about its length as well as the area enclosed by that curve. That is when the curve is a plane curve. That's what I mean by. And when it comes to surfaces, you can here talk about instead of a similar word for area for length of the curve is there here for surface, that is known as area of the surface you can think about. But when it is a closed surface, then that closed surface encloses a volume. So here you can talk about, usually one can talk about area here. Here volume enclosed by area. Volume enclosed by area. That is what I mean to say. This is important. These are important things. Enclosed by area. This is very important. So whenever, what did I say now? See clearly. So whenever I am talking about a curve, whenever we are talking about a curve, so it has endpoints, so length. When this curve, when this curve is closed, then we can think about and plane. Okay, and it is a plane curve. That is what I say, and it's a plane curve. So in such a case, what I mean to say is that it encloses a volume. So this closed plane curve encloses a volume. Sorry, encloses a region, encloses an area, a region which has rather encloses a region of some area. Fine. That's all about curve. Now when it comes to surfaces, similar idea will be there. So if I say surface, then usually I'm talking about a finite surface. So we think about area like here. When you are talking about a curve, you have length. Okay. So area you can think about. And if our surface is a closed surface, if our surface is a closed surface, then it encloses a volume. Right. Now see, like any curve can be represented as an equation involving some x, y, z, some very equations involving x, y, z. Suppose you require three equations involving x, y, z to represent a curve in three-dimensional uh, Euclidean space. To represent a surface, you require two equations involving x, y, z to represent a surface here. That's the next point. So equations will come into picture, and say like in plane, we talk about the special curves like plane curves. Plane curves, here we can talk about special surfaces called level surfaces. So whenever we come across the idea of surface, we mean that we are dealing with level surfaces. So some good objects, that is, which are in fact really extends a helping hand for all of us. Right. Okay. So now so this is all about curves. So whenever curves are there, you can talk about it is a closed curve. You can talk about perimeter, tangent vector, normal vector. Of course, and you can talk about the radius of curvature, torsion, etc., etc. But of not we are not discussing about much about those things. So in this shared PPT, all the formulas I have given here, and we have an example also I have given here. Okay. Now we directly go to, the last three slides of this presentation. So one is called Green's formula in the plane. The other is called Stokes theorem. See how the title of this one. I say some line integrals in terms of double integrals. See, we talked about multiple integrals and single integral. So remember always a line integral can either can be evaluated by reducing that into a single integral. That is one view, which I have in fact explained in the previous classes. And on the other hand, that also can be for certain type of line integrals can also be evaluated by in terms of by double integral. That is due to Green's theorem and in plane what we call, and then we can think about the surface integrals, and here the surface integral can be uh, uh, expressed in terms of a line integral. Remember, a line integral can be evaluated by reducing that into certain type of line integrals to a double integral. So a surface integral also can be integrated in terms of a double integral. That is what the Stokes theorem says. And then finally, when it comes to the Gauss divergence theorem, you have a volume integral here that can be expressed as a surface integral. That can be expressed as a surface integral. So line integral is a single integral. Green's theorem, line integral can also, some line integrals can also be expressed in terms of a double integral, and Stokes theorem, some surface integrals can be expressed in terms of line integrals. So I already told a surface, if it is open, it has boundary. Okay. And similarly, some of the volume integrals can be expressed as a surface integral. So see, please look here. When you look at this Green's theorem, you have in the left hand side integral of p dx plus q dy. C is there. So C means you have a curve there, C, and you have a curve there, and then you simply to do that one, dou q by dou x minus dou p by dou y you calculate, and then the d is represented, the is the area is the area or the region I mean enclosed by C, the closure curve C. So that is and when it comes to Stokes theorem here, please remember here curl f bar, where is the integrand here? Curl f bar dot n bar. So this n bar, see, you have a surface here. Surface, Stokes theorem is deals with always with open surfaces having a boundary. Boundary is curve. Okay. So Stokes theorem deals with you are doing integration over surfaces, open surfaces who has boundary, which has boundaries. Okay. So whenever we are talking about open surfaces, you can whenever we say it is a surface, it's a level surface, so it will be represented by phi of xyz is equal to c, say, and so simply you know how to calculate n bar. So that n bar is dou phi x I bar plus phi y j bar plus phi z k bar. Normalize it. That normalized vector is represented by n bar. That's all about Stokes theorem. And then here R bar is xi bar plus yj bar plus zk bar. Then what is C? So if our R bar is xi bar plus yj bar plus zk bar, then dr bar is dxi bar plus dyj bar plus dzk bar. So whenever I am writing, see here, integral of f bar dot r bar c. Sometimes what may happen is that the curve can be expressed in terms of a by using a parametric representation. See, whenever I say parametric representation, I'll tell you one thing here. Example, because we require these ideas here. See, suppose you think about a curve x square plus y square is equal to 1. Then, if you take x is equal to cos t, y is equal to sin t, if you put these values here, then it is satisfied. So, this is called parametric representation. And where t varies from 0 to 2 pi. So, you can move along the curve by varying t from 0 to 2 pi by 0 to 2 pi in the anti-clockwise direction. That's what it says. Fine. So this is called what we mean by parametric representation. So that if that parameter is I mean length, it could be its length or some other thing. Okay. So that is parametric representation. So when I say it is parametric, when we are moving on a curve and say it is C, then your R bar, the position vector on the along that curve. See, so x is a function of t into I bar plus y is a function of t parameter here and k bar. You can do like that. So if we look at what is dr bar by dt, you can say that x dot means dx by dt I bar plus z dot k bar. This is what I mean by. So dr bar by so see here why I'm telling you about this is that if you have f bar dot f bar dot uh, the Stokes theorem I'm talking about r bar r dash s. So here r bar dat dot s ds we mean. See here is a closed curve is there. So that is nothing but f bar dot dr bar because dr bar by this r bar dash means dr bar by ds. Okay, I'll write that also. So this is nothing but length, right? So this is the explanation. What is left hand side? What is right hand side? What are the symbols involved? I told you here. I talked particularly about n bar here. What is n bar? See here n bar I means whenever you are talking about the Stokes theorem, you have how many things you have. One is the integrand. The thing that is integrand involves f bar. So when you are dealing with Stokes theorem, you have vector field. Then the integrand is expressed in terms of f bar. In terms of f bar, I'm saying so you require a surface, a level surface. It's an open surface, please remember. Level surface. Then that surface is the enclosing curve, boundary. The enclosing curve of yes. So when you are now the surface is represented by now the surface is represented by now the surface is represented by an equation. So for this equation, from this equation, you can think about phi xi bar, phi yj bar, phi zk bar. Grade 5. This is nothing but grade 5. That is called normal vector. Now, if you normalize this means you calculate the norm. I told you how to calculate normal and multiply By this, you will get a vector that is nothing but that we usually represent by it is a unit vector, unit normal vector to the surface capital S. Okay, to the capital S, and that's what here n bar I mean. So the left hand side is a surface integral, the right hand side is a line integral. The left hand side of the integral involves f bar and curl of its curl of f bar and the unit normal vector to the surface. Yes, it's an outward normal what we call. And when it comes to the right hand side, you have the f bar as usual and a closure curve. See, and the other one is divergence theorem. Here also you have n bar. Whenever say I say here, the in divergence theorem the surface is closed and it encloses a region denoted by capital T, and so that to that surface you can think about the outward normal. Here no boundary for the region T, you have boundary here. So for that one you can surface is there, it's a closed surface. To that also you can think about the normal vector, and that unit normal vector is n bar here. Okay, so this is about the overview of the uh, standard theorems of Green's theorem of integral vector integral calculus. Yes, Green's theorem, Stokes theorem, and Gauss divergence theorem. So right now, sorry, there is an interruption here. So, yeah, so this is what we have seen so far. Quickly recalled the idea of the vector differential operator, and then uh, the idea of curves and surfaces, and then the idea of directional derivative, and the main, uh, I mean, the mean value theorems of the integral calculus, that is Green's theorem, Stokes theorem, and Gauss divergence theorem. Right. Okay. So now we'll go to, yeah, right, this problem solving session. We have discussed a good number of problems during our earlier sessions about all these things, but we need to see some more problems on directional derivatives and the applications of these three theorems. So, see for example, we take up this problem. Here, the scalar field f of x, y, z, yeah. Here, uh, the scalar field f x, y, z is given as f of x, y, z is given as x square plus 2y square plus z, right? And the point, I'm talking about the point here, the point P, point P is, they have given the point as 112, point as 112. Then what else they have given? They have given, yeah, vector. A bar is 3I bar plus 4J bar. Another thing, like A bar is 3I bar plus 4J bar. So these three things they have given. We need to find the directional derivative here. So what is directional derivative? Of f along A bar at the point P. That is the meaning here. So what will be the formula here? The formula here is, see, I am writing the formula simply. See, we have already discussed that. Yeah, right. See, this is the formula we are going to place. So in place of phi, you have f there, that's all. So, yeah. So the formula is 1 by modulus of A bar dot f. This is the formula, directional derivative formula. This is the directional derivative formula. Right? That is the directional derivative formula. So, this now we will calculate what is mod A bar. Mod A bar is mod A bar. I will take. Mod A bar is, I already told, we know it is 3 square, the coefficient of I bar and A bar, square sum of, and plus the quotient of, square of the quotient of J bar in A bar, that is 4 square. So this is equal to square root of 9 plus 16. So it is square root of 25. So positive square root, so it is 5. Right. Now we need to calculate what is grad f. Okay. So grad f means, what is the formula? Grad f formula. Grad f is fx I bar plus fy j bar plus fz k bar. This is the grade f formula. This is the grade f formula. So this is the grade f formula. So when we are talking about this gradient of f here, right, right. So What is fx? F subscript x is 2x here. So f subscript x is 2 here. F's partial derivative of f with respect to x is 2x here. Partial derivative of y, f with respect to y is, partial derivative of f with respect to y is, f with respect to y is 4y. 2y square is there, that's why it is 4y. Now, partial derivative of f with respect to z, f with respect to z, it is 1, right? Therefore, our grad f is 2xi bar plus 2yj bar plus k bar. Good. Now, we that directional derivative. I write this as some people that directional derivative of f along a bar. That time we use this symbol. So if this is the symbol, then what is that? Uh, this into a bar dot grad f. Okay, so this is equal to 1 by 5 because just now we found a bar that into the dot product. Here, what is a bar here? A bar is where is a bar? Yeah, 3 a bar plus 4j bar. 3 a bar plus 4j bar. Dot. You what is your grad f? So grad f is 2xi bar plus 2yj bar plus k bar. K bar. So this is equal to 1 by 5, okay, into 6x plus 8y. That is the thing. 6x plus 8y. So this is the dot product there. So this is now we want to this directional derivative. We want this directional derivative at which point there is another point is given here. That point is P. Yeah, 112. So that is 112. So at this point we want the directional derivative. So simply we have calculated this on the top 1 by 5 6x plus 8y. So 1 by 5 6x plus 8y at p is equal to 112. So this is 1 by 5 to 1 into 6 plus 8 into 1. It is. So we have 14 by 5. This is the directional derivative. So like this directional derivative can be computed. Like this directional derivative can be computed. We used the formula and we found the directional derivative. Then we go to some more representative problems. Okay, which we have not done. That part only I will cover. Yeah, see here. For the spherical surface, x square plus y square plus z square is equal to 1. The unit outward normal vector at the point. So, see here. So, what is the given surface here? The given surface is a level surface. Yeah, it's a level surface. Its phi xyz is x square plus y square plus z square, and of course this is equal to c, say, so this is equal to 1 there. So what is the this is what is the unit normal vector, outward normal vector? So the simple thing, the formula is n bar or n cap, people, right? 1 by grad phi modulus and grad phi. So what is grad phi? Grade phi is grade phi is phi xi bar dou f by dou phi by dou x, that is phi y by j bar plus phi z k bar. So what is phi x here? Phi x is dou phi by dou x, that is dou phi by dou x, that's 2x, dou phi by dou y is 2y, dou phi by dou z is 2z. So this is equal to 2xi bar plus 2yj bar k bar. So now modulus of grade phi square root of 2x whole square plus 2y whole square plus 2z whole square. So this is nothing but 2 into square root of x square plus y square plus z square. On the other hand, this value is anyway 1. Right. This I say square root of x square plus y square because we are on the surface. We are on the surface. It is okay, right? We are on the surface. Fine, good. Okay. This is our okay. Right. Right. We do one thing. All right. Now, at what point we are asking for to draw the normal? At what point we are asked to draw the normal? 1 by root 2, 1 by root 2, 0. 1 by root, remember 1 by root 2, 1 by root 2 is there on the surface. If you substitute these x in place of x, 1 by root 2, in place of y, 1 by root 2, and in place of z, if you take 0, then this, okay, in the above, then at that point we are talking about, so we are trying to draw n bar at this point. Okay, so this is 2 into square root of x square plus y square plus z square is modulus, in fact. 1 by root 2, 1 by root 2. I am talking about this modulus 0. So it is coming as 2, right? N bar is 2. I mean, modulus of n bar is 2. See here, here it is right, modulus of n bar. So unit normal vector now is 1 by 2 grade phi. What is grade phi? 2x a bar you are right. And this also at 1 by root 2, 1 by root 2, 0. So you have 1 by root 2 I bar plus 1 by root 2, because here, oh, root 2 I bar, sorry. Okay, now this normal vector at 1 by root 2 1 by root 2 0. So this is our n bar. This is our n bar. Unit normal vector. This at gives us 1 by root 2 I bar plus 1 by root 2 j bar. That's all. So this is the unit normal vector to the surface at 1 by root 2 1 by root 2. Right. Now we go for yeah, a good problem. Okay, just a minute. Some more problems. I think I'm looking for some problems uh, on divergence theorem, etc. And Green's theorem we have done. That's why yeah, here Stokes theorem connects everything. These things also we have done. Some problem on okay, I think this collection not much related to these three theorems are there. We'll see some sample problem I will do and then we'll close. Okay, we'll look at the 41st, 41 problem. That's ideally thing. Right. Given f bar, right, this is good. So here, given what is f bar? F bar is ZAX bar. Here, AX bar means unit vector along x, and AY bar means unit vector along y, and AZ bar means unit vector along z axis. So you can understand like that. So uh, z into I bar plus x into j bar plus y into k bar, I think, right? Right. So now what is the surface? Surface is x square plus y square plus z square is equal to surface I am talking about 1. It is equal to 1. And see, he is putting z greater than equal to 0. Z greater than equal to 0. Right. Then what we need to calculate? Need to calculate. Need to calculate integral. Need to calculate integral curl f bar, okay, ds. Curl f bar, there is, yeah, good, dot ds bar, it's very important. Ds bar, okay, good, this is the thing. Okay, so when we go to Stokes theorem, okay, I will go to that PPT part. Yes. See here, if you go to this part, curl f bar is there and dot ds bar is there. So, see, in our theorem, we need to find this actually. So, instead of yes, we have, okay, what is there in that? A bar is there. Some people write S bar, some people write A bar, A for area, surface. So, this is, need to find this actually. Curl of F bar dot N bar dA. You please remember this. So, whenever we have ds bar, this object can be treated as n bar dA, where n bar is the unit outward normal. Okay, good. Now, this needs to be evaluated. But remember here, this is an application of Stokes theorem. It is nothing but f bar dot dr bar. That's all. You can write like this: f bar dot dr bar along C. Please remember along C. What is the collection? See how S and C are connected here. So we have x axis, y axis, z axis. Okay, and we are talking about a surface here. It is clearly sphere. When z is greater than or equal to 0 means upper portion above xy plane. So it will be like this. This is the sphere they are talking. What is the equation of this? It is x square plus y square plus z square is equal to 1. Is equal to 1. Yeah, right. Now, where is this C? So our surface is, please remember, our surface is this. This is our surface. This is our surface. Then where is our C? I'll come to that C part. So this is our C. This C, it is a circle centered at origin with radius 1. So it is nothing but x square plus y in xy plane, that 1 comma z is equal to 0. Please remember, z is equal to 0. You are in the xy plane. That is your C. Where, in which plane you are? You are in on z is equal to 0, that is xy plane. And we are talking about the unit circle centered at origin there. That's our C. Okay. Now once determined, now you can directly apply Stokes theorem to evaluate this integral. All right. So where is our right? So f bar dot dr bar, now you have to see. So what is our f bar? Our f bar is this. Okay, good. Our f bar is where is that? Yeah, Zi bar plus xj bar plus yk bar. Dr bar dot dr bar I told what is that? I bar dx plus j bar dy plus k bar dz. Yeah, this is the one. And you have the C there. Okay, that is a closed curve C. See, always remember our R bar is xi bar plus yj bar plus zk bar. Okay, then our dr bar is dxi bar plus dyj bar plus dzk bar. This is always fixed, right? So this is our dr bar. Now, if we calculate these things, so this is equal to how the integrand looks like now. Okay, z dx plus x dy plus y dz. Remember, this is a line integral. Now, in this integrand, you have x, y, z, but all are in fact interlinked. You need to convert this into a single integral. That's what I told you. Like, how can we evaluate line integrals? We can evaluate line integrals by converting them into single integrals or double integrals. But we are going to convert this into a single integral. That is easy. How? How that can be? Because that being a circle, you have a parametric form here for C. So for your C, x square plus y square is equal to 1 is there, okay, and z is 0. That is our curve. So for this one, you are on the curve. Please remember, we are on the curve. So this part can be reviewed as x is cos t, y is sin t, okay. Then what is our t? T is in, yeah, we are moving along C in the counterclockwise direction. So 0 to 2 pi. So what is dx here? Dx is minus sin t dt. What is dy here? Dy is cos t dt. That's all. You can substitute these things here. One can substitute these things here. How when we substitute these things here, right? Okay, right. So is equal to what is our z? Z is 0. So I write integral here 0 into dx, or dx is minus sin t dt. Okay, plus x is cos t. What is dy? Y is sin t, therefore dy is cos t dt. Okay, plus y is sin t into your dz is 0. Dz is 0. And your t varies from 0 to 2 pi. See, we convert the whole thing into an integral involving one variable t. So this is integral 0 to 2 pi, okay, cos square t dt, cos square t dt. So cos square t is nothing but 1 plus 2 cos t, 1 plus 2 cos t 2t by 2. So 1 by 2, 0 to 2 pi, 1 plus cos 2t dt. So this is equal to 1 by 2. All right. You have what is the integral here? T plus sine 2t, t plus sine 2t by 2. And our t varies from 0 to 2. So you will get 1 by 2, 2 pi, pi. So our line integral is this. Our line integral is this. So this is its value is pi. Okay, so we used here Stokes theorem. That's what I'm saying. So good application for Stokes theorem. If you evaluate, see the if you want to evaluate this integral, I mean this line. See what we have done. We are asked to calculate. We are asked to compute. We are asked to compute the last one. No, not this one. Yeah, we are asked to compute curl of f bar dot ds bar. We applied Stokes theorem here. We are not doing that by see how surface integrals can be done. Just simply reduce to line integral. That line integral we have done here. That conversion we have done here. Okay. In order to apply that the idea of line integral, what is C need to be determined, and that we have found, and that curve parametric representation we have written, and we knew it, and thereby we got the answer as well. So this is all about the calculus, and if one more is there, we can see. I think we have covered good. Okay, gradient of scalar field. Gradient of scalar field is a vector. See, that's such simple things also they are asking. Anything application I'm thinking about some application. See here also, okay, that's about Stokes theorem. If you, I will do one more problem. mm, on directional derivative and close this one. Okay. Ah, see this uh, on directional derivative and close this. So quickly, what is our fxyz? I write as no problem. You can take fxyz even if they give us two variables. You can take that. Consider it a three variable problem. Xy by root 2 into x plus y. Okay, this is our f. Then where is your point? That point I used to say that point P is 1 1. The other is not giving, so it is 0. That coordinate is 0. We are on the plane, that's why I'm taking that. And now the direction at the angle pi by 4. See, at the angle pi by 4 means that is this vector I'm talking about. We are in the xy plane. It is 1 by root 2 I bar plus 1 by root 2 j bar. How can I say this one? That's the question. So it is simple. See, when you are in xy plane, when you are in xy plane, the vector that makes 45 degrees, okay, is represented by x is equal to y line. So any vector along this line is represented by x into, see, any vector along this one. So it is r bar. R bar is xi bar, yj bar plus zk bar. Is it right? This is our. But x is equal to y. Please always remember you are in the in the xy plane. So here, if I substitute those things, xi bar plus xj bar, because y is equal to x, 0 into k bar. So we have x into, you have x into I bar plus j bar simply. Now if we want unit vector, I mean, what did he say? He is talking about unit vector, I think. Where is his unit vector? In the direction of the unit vector at an angle. Sorry, unit vector at an angle pi by 4 with y-axis. Right. That is with that angle with y-axis pi by 4 means one need to take, please, here, just, right, pi by 4 y-axis means you need to take this one, 45 degrees. So this line is x is equal to minus y. X is equal to minus y. So if I take x is equal to minus y here, so wherever x is there, you can put y is there, minus x you can put here. So sorry, not here. Right. So this is good. So this is the one. So now my a bar unit vector at, therefore r bar by r. R bar by r is, r means modulus of r bar here. So 1 by modulus of that is square root of x square plus minus x square into xi bar minus xj bar, right? So this is 2x here. X square plus x square is 2x. I mean 2x square. So it is 1 by root 2. Right, good. So this is nothing but 1 by root 2 into I bar minus j bar. Now we calculate grad f. Where is the grad f here? Grad f we calculate because we require grad f here. So grad f is, okay, grad f is, closing this, grad f is, where is that? Yeah, grad f is 1 by root 2 2xy, 1 by root 2 2xy, 1 by root 2 2xy, 1 by root 2 2xy I bar plus 1 by root 2. Again for that also you have, because for this you have y square. So 1 by root 2 y square, or 2 will be there, right? No? 2x, 1 by 2 will be there. Good. So 2xy j bar. That's all. Right. So this amounts to, this is equal to, okay, root 2 xy I bar plus j bar. Good. Okay. Now our thing, that is the directional derivative part. Okay. So this is the convention I have followed. You have a bar at 110. That is important. At 110. At 110. Okay. Is equal to, quickly I'll close, is equal to that unit vector. Where is that unit vector? We have calculated. Yeah. 1 by root 2 I bar minus j bar dot dot this grad f root 2 xy I bar plus j bar. So this is nothing but you have xy. Okay, I bar dot I bar is 1 minus 1. So it is, you are getting 0 here. So whatever it may be, we are getting right. So this is all about the vector calculus we have discussed. Okay, in the next session, we quickly follow some problems as we introduce the idea of numerical solutions to equations and ODE, and we quickly numerical integration. We talk about those things in the next session. Okay, so this is all about for today. Thank you.